We had looked into the constant pressure expansion or compression process with regards to the boundary work. There's a numerical associated with this problem. The first part, this is the statement of the numerical, which says the piston cylinder device contains saturated water vapor that is maintained at a constant pressure of 300 kilopascal. And then it says that a resistance heater within the cylinder is turned on. And as a result of this heater being turned on, the piston cylinder assembly does some work. And at the same time, there is a heat loss of 3.7 kilojoules that takes place. The first part, which is the part we had already looked into in our last is that show that for a boundary WB and the change in internal energy can be combined into one term enthalpy for to the first part, which says that for a closed stationary system you have the equation Q minus W is essentially equal to delta U. This is the statement for a closed stationary system. Is it clear so far? Is this expression clear so far?
Yes, sir.
All right. Now we further say that we can split W into W other, which is anything, any work other than the boundary work and the boundary work. So Q minus W could be split into work other and boundary work, essentially WU. And for boundary work, the expression is integral 1 to 2 PdV. And for a constant pressure process, we can represent PdV as P naught into V2 minus V1 for a constant pressure process. So we can write this equation Q minus W other work is and for a boundary work we could represent V1 is essentially equal to delta U. Now if I take this expression onto that right hand side, we will see that Q minus work other is essentially equal to U2 plus P1 P2 V2 minus U1 plus P1 V1. Since P naught is equal to P2 is equals to P1, I can write this expression. This is for a constant pressure. And I know that enthalpy is essentially a combination property of U plus PV, the internal energy plus the flow work. I can write it as Q minus work other is essentially equal to H2 minus H1. So this is where we have combined the internal energy and the boundary work in terms of enthalpy. This is the expression we have already seen. So over here in this expression, you have electrical work which is coming Q out is going out of the system and there is boundary work. And once I move boundary work onto that right hand side, I can say the electrical work in minus Q out is essentially equal to change in enthalpy of the system or mass multiplied by specific enthalpies, difference in specific enthalpies. Is it clear? Is it clear so far? Yes,
Yes, sir.
no? All right. Now it says that once you have this done, you have to find out the next thing is for the data given to you have to determine the final temperature of the steam. This is your system. It says that initially your system is existing as saturated vapor at 300 kilopascal. So if you see 300 kilopascal saturated vapor, this is your first state. Now it says as a result of this resistance heating and some heat coming out of the system, your system moves to state 2. For the moment, we can assume that this state 2 is over here. It could either on the right hand side of state 1 or on the left hand side of state 1. Why? Because the process is taking place at constant pressure of 300 kilopascal. So the constant pressure line is this line 300 kilopascal. One could either move to 2 or it could move towards the inside of the or to the left side of the state 1. For the moment I have assumed that it has moved to state 2. Now I have to determine the final temperature of the steam. For this state, which is state 1, I know that my pressure P1 is 300 kilopascal and my X value is 1 or the quality value is 1. For state 2, the only thing I know is P2 is 300 kilopascal. I don't have any other property to find the temperature from the table. So I have to identify the region as well as I have to find out the second property to find the corresponding temperature at state 2. Is it clear so far?
Yes, sir.
All right. In order to do so, this is the information given to me. Mass is given to me as 25 gram. The initial condition is saturated vapor. Pressure P1, P2 is 300 kilopascal. Some heat is moving out of the system. Electrical energy is being supplied to the system, and the piston is moving as a result. This is the equation that we had derived for the system. That work electrical in, since it's coming into system, minus Q out, which is the heat transfer moving out of the system, is essentially equal to M multiplied by the change in specific enthalpy. This is the equation for the system I am considering. Now, first look into the electrical work. It has been given to me that the current is 0.2 amperes, voltage is 120 volts, and it is being supplied for 5 minutes. If I have to find out the electrical work is simply what? W electrical into the system. W electrical into the system is essentially what? VIT. This is essentially the electrical energy that is being supplied to the system. So V is 120 volts, current is 0.2 amperes, and since I am considering in joules, I have to convert the time into seconds. And once I divide it by 1000, I would have 7.2 kilojoules. This is the work electrical into the system. Clear enough?
Yes, sir.
All
Yes,
right.
sir.
If you look at the expression, it says work electrical in minus Q out is essentially equal to change in enthalpy of the system. Work electrical in is known to you. If you go back, you would come to know that Q out or Q moving out of the system is 3.7 kilojoules. So this is what you calculated, the electrical work. This is given to you. Delta H is essentially equal to mass multiplied by H2 minus H1. Now, if this is given to me, or this I have calculated, this is given to me, mass is given to me, H2 and H1 are unknown to me. Can I find any one of the two, H2 or H1? Can I find any one of the properties, H2 or H1?
So change in delta H find out sir.
चेंज इन डेल्टा एच फाइंड हो सकता है, H1 फाइंड आउट नहीं हो सकता.
So
H1 is
initial
what?
state का नहीं होता.
H1 is what? It is Hg at 300 kilopascal. You are talking about steam tables. H1 is what? H1 is Hg. It is X equals to 1 or it is saturated vapor. And saturated vapor at 300 kilopascal. Can you find out from the table? Yes, no?
Yes
Yes,
sir.
sir.
So if you go to the table A5 for 300 kilopascal, you would see that the enthalpy value Hg, this is your Hg. This is for saturated vapor and your state is saturated vapor at state 1. So you can find out the value of H1 as Hg against 300 kilopascal. Clear enough?
Yes, sir.
All right. Moving on, if I plug in all the values, state 1 again H1 is Hg at 300 kilopascal, which is 27424.9 kilojoules per kg. If I plug in this value into my equation, the only thing unknown to me was H2. Now I have found out H2. Can you tell me that my state 2, whether it would be in the superheated vapor region, in the mixed region, or in the compressed liquid region?
Super heated.
Very good. Why? Because H2 is essentially greater than Hg. So essentially my system would be in superheated vapor region. So my assumption of system moving from super saturated vapor to superheated vapor is correct. Clear enough? Is this clear?
Yes, sir. Yes, sir.
All right. So now if I write down the states over here for my system, at state 1, my pressure is 300 kilopascal and my state is saturated vapor, or X is equals to 1. And at state 2, my pressure is 300 kilopascal and my H2 value is 2864.9 kilojoules per kg, and I am in superheated vapor region. So using these this information for state 2, can I find out the temperature for my system? The final temperature, if I want to find out the T2, can I find it out?
यस सर।
How?
सर वो टेबल बना के जो दरम्यान वाली क्या कहते हैं इंटरपोलेशन से।
Which table to use? Which table do I have to use?
सर ए
Pressure वाला
सिक्स
टेबल।
यूज करें।
Since we are talking about the superheated vapor, the table A6 is for superheated, so we'll use table A6. For table A6, I'll go to the pressure which says zero point 0.3 megapascal or 300 kilopascal. For this table, this is basically specific volume, this is internal energy, this is enthalpy, and this is entropy. So for this table, I'll go to the enthalpy value for this pressure. I'll go to the enthalpy value for 2864.9. Now I see over here under the enthalpy table, I see over here the value 2865.9, which is roughly the same value. So in this case, I can avoid interpolation. It's my choice. I can still do the interpolation between 2865.9 and 27276.1.2. I can do the interpolation between these two to find out my temperature between 150 and 200 degrees centigrade. But since the value is very close to 2864.9, I'll not do the interpolation to save my time. I'll consider 200 to be my temperature. Clear enough? So I'll say that P2 and H2 are given to me. For these two conditions, superheated vapor, my temperature is 200 degrees centigrade. Is it clear?
यस सर।
All right. Now moving on, I have a schematic which says that Q minus work other minus boundary work is equal to delta U. And I can combine these two into enthalpy, but I have to make sure that when I'm using this equation, Q minus work other equals to delta H, I am considering the process where P is equals to constant. So for a closed system which is undergoing a quasi-equilibrium process, pressure is constant. You can say that internal energy plus boundary work is essentially equal to delta H. However, this relation is not valid for valid for processes in which the pressure does not remain constant. So this expression is only valid for constant pressure processes. This is one thing. Secondly, whenever you have expansion in vacuum, when you have vacuum pressure, your boundary work is essentially zero. So any expansion of your system in vacuum would mean that your work done is essentially, remember this point. So expansion against vacuum and work, and thus no energy transfer takes place in terms of work. Moving on, we have another example which says that a rigid tank is essentially divided into two equal partition. Initially, one side of the tank contains 5 kg of water at 200 kilopascal and 25 degrees centigrade, and the other side is evacuated. That means it's vacuum over there. Partition is then removed and the water expands into the entire tank. As the water expands, the temperature goes down and there is an heat exchange which is allowed with the surroundings until the temperature in the tank returns to the initial value of 25 degrees centigrade. There is no heat transfer associated with this process. You have this tank with you, which contains water. Mass is 5 kg, pressure and temperature is given to you. Once the partition is reached, the heat transfer takes place, and at the final state, your volume is increased and your temperature increases. This is the information given to you. The first thing is that you have to determine the final volume. For that, this is the pressure specification diagram. Sorry. So this is your pressure specific volume diagram or a plot. In this plot, initially your system is at 200 kilopascal. This line is a constant temperature line of 25 degrees centigrade. So your system is over here, point 1, which corresponds to 200 kilopascal. So for 25 degrees centigrade, the saturation pressure is, this pressure is 3.1698. This is the saturation pressure at 25 degrees centigrade, or this is this pressure, 3.16. Now, if you this information with you, is your water at state 1 compressed liquid, saturated vapor, superheated vapor, or mixed region? For state 1, where your pressure is 200 kilopascal, your temperature is 25 degrees centigrade. Your pressure is greater than the saturation pressure at 25 degrees centigrade. Are you in the superheated region, mixed region, or in compressed liquid region for state 1?
So
Compressed.
compressed.
You are in the compressed liquid region because your pressure is greater than the saturation pressure. So for compressed liquid region, the approximation is that the specific volume at state 1 can be approximated as Vf at the same temperature, which is 25 degrees centigrade. So this is the approximation that you can use for compressed liquid, if you remember. Now, if you have to use this approximation, for this approximation, you know you have to use table A4. In the table A4, for 25 degrees centigrade, you will use the value of Vf, and that comes out to be 0.001 meters cube per kg. If you know the specific volume at state 1, can you find out the volume at state 1? the mass is given to you, you
Yes, sir.
simply have to,
Yes,
very
sir.
good. So you simply have to multiply the mass with the specific volume. So this is the volume at your state one. Now, how can you find out the final volume of the tank? Anybody, how can you find out the final volume of the tank?
The final pressure पे सर जो specific वॉल्यूम होगा सर गैस का सर वहाँ से स्पेसिफिक वॉल्यूम को वेट से मल्टीप्लाई कर देंगे सर।
Does this information give you any help? A rigid tank is divided into two equal parts by partition. Initially आपका आधा टैंक occupied है.
सर तो सब
जी
वॉल्यूम
सॉरी.
सर जो इनिशियल सर जो P1 पे सर जो वॉल्यूम होगा सर P2 को उसका डबल वॉल्यूम हो जाएगा सर।
Very
तो वहाँ
good.
से
So the final volume of the tank, which is at state 2, is what? 2 multiplied by the initial volume, which is at state 1, and this comes out to be 0.01 meter cube. All right. So your final volume is double the initial volume. And if you know the final volume, if the final volume is known to you, can you find out the specific volume associated with this? Since the mass remains
yes
constant, so the volume at specific volume at state 2 would be what? V2 divided by the mass, which is 5 kg. So this is your specific volume at final state. Clear enough? Is
Yes,
this
sir.
point clear? All right. So now if I try to draw the schematic, this is the pressure volume plot. This is P, this is V. This is the constant temperature line of 25 degrees centigrade. My initial volume and specific volume tells me that my system is at 200 kilopascal and it is in the compressed liquid region. This is the saturation pressure of 3.16. I say that my volume at state 2 is 0.02. Now, can I find out whether I am in compressed liquid mixed region or superheated region for state 2? I have to identify the region for state 2. Can I find it out? स्टेट 2 पे मेरा टेम्परेचर क्या है? 25 डिग्री सेंटीग्रेड है. स्पेसिफिक वॉल्यूम क्या है? 0.002 है. If I have these two properties known to me, I'll go to 25 degrees centigrade, table A4. Vf is 0.001 and Vg is 43.40 from table A4. Can I find out whether I am in mixed region, compressed liquid region or superheated region?
सर मिक्स रीजन
Very good. Why? Because your the specific volume V2 is greater than Vf and less than Vg, so you are in the saturated liquid vapor mixture at the final state. And thus the pressure is the saturation pressure. So your pressure at final stage would be the saturation pressure at 25 degrees centigrade, which is 3.1698, which is this pressure. Clear enough? ये चीज clear है?
Yes,
यस
sir.
सर
So at state 2, you are somewhere in this mixed region, and this is your state 2. Now, the third thing was to find out the heat transfer that took place. For heat transfer, before we begin into that, this is the process. So this is my process from 1 to 2. This is how the process took place. I moved from compressed liquid region to mixed region as a result of the heat transfer to the system. Anyways, if I want to find out the net heat transfer, I know the equation for a closed system is Q in equals to delta U. The equation is Q plus W in minus Q out minus W out is equal to change in energy of the system. I know there is no work out, there is no heat which is flowing out of the system, there is no work done on the system. So essentially Q in is equal to delta U, or it is essentially equal to mass multiplied by U2 minus U1. This is my Q in. Mass is known to me. I need to have U2 and U1 to find out the heat transfer to the system. So how can I find out U2 and U1? If I need to find out U2 and U1, how can I find it out? The internal energy at state 1 and the internal energy at state 2. Any idea how can I find it out? For state 1, I am in compressed liquid region. So for compressed liquid region, U can be approximated as UF at the temperature which is 25 degrees centigrade. So U1 is essentially what? U1 is essentially UF at 25 degrees centigrade, which comes out to be 104.83 kilojoules per kg. Is it clear so far?
Yes, sir.
All right. In order to find U2, I know I am in mixed region. I need to have an expression or value of X in order to find out U2. So if you remember, the U value or the average value or any property value is essentially UF plus X UFG, or V average is equals to VF plus X VFG. I have the value V2 is V average. So V2 is known to me. Vf, if this is the constant temperature line of 25 degrees centigrade, Vf I can find out from the table. Similarly, Vg I can find out the table, and Vfg would essentially be the difference of Vg minus Vf at 25 degrees centigrade. So the quality or X can be determined from V2, which is V average, Vf at 25 degrees centigrade, and Vfg for 25 degrees centigrade would give me the value of X2. Once I have the value of X2, I can find out the value of U2, which would essentially be equal to UF at 25 degrees centigrade plus X multiplied by UFG at 25 degrees centigrade. So UF at 25 degrees centigrade is known to me, 104.83. X value I have found out from this equation, and this is UFG at 25 degrees centigrade. Once I have the U2 and U1 known to me, I'll plug in it into this equation, and this would be mass multiplied by U1, U2 minus U1, and this would give me the heat transfer that took place during the process. All right. Any confusions with regards to this process? Anything which you have not understood? Let me know right now so that I could explain it again. Or is it clear? Yes, no, are you still there?
Yes,
Clear.
sir, clear.
All right. Now the specific heats. Will be moving into the understanding of specific heats. It says that if you have 1 kg of iron and 1 kg of water, and you have to raise the temperature of both from 20 to 30 degrees centigrade. In one case, iron would take 4.5 kilojoules of energy, whereas the water would take roughly 10 times the same energy, which is 41.8. So that means the energy that can be contained within a system is is dependent upon that system or that material. Having this in mind, we have defined that uh, the term specific heat, which is the energy required to raise the temperature mass of 1 kg by 1 degree centigrade in a specified way. So specific heat is the energy required to raise the temperature of a unit mass of a body by 1 degree in a specified manner. When I say in a specified manner, I refer to two different things or two different processes. One is the energy required to raise the temperature of a unit mass of a substance by 1 degree as the constant volume is maintained. So at constant volume, the energy required to raise the temperature of a body of having one unit mass by 1 degree is basically defined as CV, which is the specific heat at constant volume. And another way is the energy required to raise the temperature of unit mass of a substance by 1 degree under the constant pressure process. This is known as CP or specific heat at constant pressure. Now, if I look at the two processes over here, when the volume is constant, and if you are having a mass of 1 kg, you change the temperature by 1 degree, you have to provide 3.12 kilojoules of energy. This is for any substance. Uh, let's say I guess it's helium. But for the same substance, if you have to provide the if you have to raise the temperature of 1 degree by um, keeping the mass as 1 kg and your pressure is constant, you would have to provide essentially more energy. Why? Because in order to keep the pressure same, your piston would move from 1 to 2. So there would be some boundary work associated with the constant pressure process. Now this is basically CP or constant pressure heat, and this is your CV, which is constant volume specific heat. Again for the helium gas. Considering the two, uh, why do you think CP is always greater than CV? One thing, whether it's true or not, and why do you think CP would always be greater than CV?
सीवी में तो सर उसकी सिर्फ इंटरनल एनर्जी चेंज हो रही है और सीपी में उसका साथ साथ वर्क भी हो रहा है तो वो एडिशनल
Very good. So in CV, I'll not go to internal energy at the moment, but yes, CV, it does not involve, since dV is equals to 0, so your PdV or boundary work is essentially 0. Your system does not have to do any work against the movement of the boundary. But in case of CP, you have the additional work which is associated with the movement of boundary which is involved. So you need to provide more energy to the system in order to cater for the movement of boundary from state 1 to state 2. So CP would always be higher as it involves the boundary work. Clear enough? Moving on,
यस
specific heat in terms of other thermodynamic properties. You have to develop a relationship between specific heat and other thermodynamic properties. So you consider a closed stationary system undergoing a constant volume process. That is, no compression or expansion work is involved. So the energy equation should be E in minus E out is equal to change in energy of the system. So that means the differential energy coming into the system minus differential energy moving out of the system is equal to the change in internal energy of the system. Now, this net energy which is moving into the system is what? It is nothing but CV multiplied by dt. So the left hand side of the equation represents the net amount of energy that is transferred to the system. From the derivation of CV, this energy must be equal to CV dt. CV is basically energy per unit mass per change in temperature. So energy per unit mass for change in temperature dt would essentially be equal to kilojoules per kg. So CV dt is basically the net amount of energy that is flowing into the system. Using this in mind, you will have that for constant volume process, CVDT is essentially nothing but the change in internal energy at constant volume. And similarly, the CPDT is basically nothing but change in enthalpy of the system at constant pressure. This could also be represented in formal definitions which says that CV is partial differential of U divided by partial differential of T at constant volume. And similarly, Cp is nothing but partial differential of enthalpy with regards to partial change in temperature at constant pressure. Now, since U is a property, T is a property, enthalpy is a property, I would say that Cv and Cp are also properties of the system. And Cv is related to the internal energy of the system, whereas Cp is related to the enthalpy changes in the system. And the common unit is kilojoules per kg per Kelvin or per degree centigrade. Is there any difference between the two units? Are these
सर
units
पर कैलोरी
identical?
वाला SI यूनिट है.
No, I mean in terms of values.
No, sir.
Why?
यस सर
Because
आएगा.
there isn't any
नो सर
difference
सर सेम हो.
because you are representing the change. All right.
तो यस सर दोनों चेंज सेम होगा.
Very good. So moving on, now you have to relate the internal energy enthalpy and specific heats of ideal gases. So I'll not go into the details of this, but Joule showed that internal energy for an ideal gas is only the function of the temperature. In such a case, you have the definition that enthalpy you have defined previously as the enthalpy is a function of internal energy and the boundary work, which is PV. Since you are representing per unit mass, I have represented small u and specific volume. And the ideal gas equation says that PV is equals to RT. Now, if you replace in this equation PV with H and U, which is enthalpy and internal energy, you'll have an equation which says that for an ideal gas, enthalpy is equal to U plus RT. For an ideal gas, Joule had showed that U is a function of temperature, R is a constant, and you have a temperature. So essentially, H is also, or enthalpy for an ideal gas is also a function of temperature. In such a way, so you say that internal energy is a function of temperature, enthalpy is a function of temperature, change in internal energy is Cv dt multiplied by dt, change in enthalpy is Cp, which is a function of temperature multiplied by dt. So, or for an ideal gas, enthalpy, internal energy, Cv and Cp, all four are function of temperatures only in an ideal gas. And internal energy change and enthalpy of an internal energy and enthalpy change of an ideal gas could be expressed as this: delta U is U2 minus U1 or integral 1 to 2 CVT dt. CVT is a function of temperature. Similarly, enthalpy change of an ideal gas could be expressed as 1 to 2 integral of Cp dt, where Cp is the function of temperature only. So far, is it clear or is there any doubt?
Clear, sir.
All right. Now, this was for the ideal gas. For the real gases, they behave as ideal gas at low pressures, and therefore the specific heats of real gases depend on temperature only at low pressures. And for real gases, the specific heats are defined as ideal gas specific heats or zero pressure specific heats by the simple Cp naught and Cv naught. And here's the temperature, here's the relationship of temperature versus the ideal gas specific heat at constant volume for real gases, and this is a function of temperature only. For monatomic gases, the deviation is uh, more uh, for diatomic gases. For monatomic gases, the variation roughly remains the same with regard to temperature. The essential thing over here is now you know that Cp and Cv, they are a function of temperature only for ideal gases or real gases that behave ideally. In order to calculate delta U and delta H, you need to have a relationship of Cp and Cv with temperature. There are three ways in which you can determine the or you can solve the integral delta u is equals to cvt dt from t1 to t2, or similarly delta h is equals to t1 to t2 cp t dt. There are three ways to solve uh, and find out the change in internal energy and enthalpy uh, for ideal gases or real gases that approaches ideal gas behavior. The simplest thing is you have a relationship of Cv with temperature or Cp with temperature in order to integrate. This is the simplest thing. And for if you look at the ideal gas tables, for example, if you look at the ideal gas table A17, A2C, sorry, if you look at the table A to C, you will have the gases mentioned on the left hand side and the relationship of Cp. Cp is mentioned A, B, C, and T. These are the constants which are mentioned against each gas. For nitrogen, A is this, B is this, C is this, and D is this. This is the temperature range for which these constants are valid. If you plug in these constants into this equation, you will have essentially a equation which is between Cp and temperature. So you can plug in that relationship of Cpt in the equation and integrate with regards to dt from T1 to T2. But this would give you delta H for that specific gas between T2 and T2, T1 and T2. But the calculations is very hectic. This is one way to find out delta H or delta U using the exact relationship between Cp and temperature to find out the integral Cpt dt. Another way is that someone has already uh, performed the integration for u and tabulated the value of u and h for a number of gases. If you look at the table for air, which is the ideal gas table A17, you would see the ideal gas table A17 for air. The temperature is given, and in front of temperature, you have internal energy and enthalpy values are given. In this table, you have assumed the in the preparation of the table, the integration has been done from 0 to the respective temperatures. Cp T dt. This has already been done for you. So this would essentially be equal to delta H for temperature between 0 Kelvin to the temperature T Kelvin. At 0 Kelvin, the internal energy and enthalpy are assumed to be 0 as a reference value. And all the integrations have been done for you. So let's say if I talk about 300 and the value is 214, it means that from 0 to 300 Kelvin, the value of CVT dt for air is essentially 214.07. Similarly, if I look at 3110, I would say that from 0 to 3110, the value of CVT dt is essentially double to 1.25 kilojoules per kg. So if I want to find out the change in enthalpy from 300 to 310 CVT dt, or which is essentially change in enthalpy, if I want to find out this value, I would essentially use the value of 214 and 221 and take the difference. That means 221.25 minus 214.07 would give me the change in internal energy of air moves from to 310 Kelvin. I don't have to do the integration from 300 to 310 CVT dt. I don't have to do it myself. I can use to find out the value. Is it clear? Is this point clear to you?
Yes, sir.
This is table A17. So the first thing is you can use table A to C, where you'll have the relationship between Cp and Cv, or Cp with temperature, and you can do the integration by plugging that relationship, or you can use the already integrated data for you in the ideal gas tables for the specific gas. For air, the ideal gas table is A17. You can use the integrated values from 0 to the specific temperatures to find out the values. And this is the ideal gas table. And the third thing is approximation. Your system moved from state 1 to state 2. State 1, the temperature is T1, state 2, the temperature is T2. You can do the integration by taking the average temperature, which is the middle of the two, and finding out the Cp value from the table. So if you go to the internal energy enthalpy value, so U2 minus U1, initially it was U2 minus U1 is basically integral of 1 to 2 C, which is Cv, which is a function of temperature, integrate with respect to dt. If I take the average value, I'll say that average value is constant. So C average integral 1 to 2 dt is left. So this would essentially become C average T2 minus T1. And this average value is what? It is the average value of C at T2 plus T1 divided by 2. So this is the average temperature at which you'll have this average value. Similarly for Cp, again, these relationships are valid for any kind of process. Three ways of calculating delta U and delta H for ideal gas or real gases behaving ideally. Number one, you use the most accurate method, which is using table A to C and integrating the number one is using table specific ideal gas tables. For air it is A17, so you are using the tabulated value of U and H, which is the most accurate when tables are readily available for you. The second one is by using the CV or CP relationships, which is table A to C, as a function of temperature and performing the integrations yourself, which is very inconvenient, but it is very accurate. Number third method is by using the average specific heats. This is very simple, in which you have to use the property tables. When the property tables are not available to you, you will simply go to table A to B, and for the specific gas, once you have the temperature, you will read the Cp value in front of it. These are reasonably accurate uh, if the temperature interval for which the average value is taken is not very large. So this is from the table, which is in case of air, it is table A17. This is again using the relationship between Cv and Cp for and temperature, which is table A to C. And this is the average value that you can take from table A to B if you know the average temperature. Clear so far?